Welcome to the Problems Channel Season 3, Episode 28, the episode which I titled In Like a Line, Out Like a Lamp, because in this episode we will evaluate a certain trigonometric sum, which at first blush comes across as quite scary, but which with a clever idea can be transformed into a quite docile little lamp. Before we deep dive into the underlying transformation, as a traditional and friendly reminder, if you're joining our channel mid-season, especially after the Season 1 and Season 2, first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is for you to go to the homepage of our channel, and at the top of that page in the channel's trailer section find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because that way you will quickly ascertain who we are and what we do. And in the lightning round on this channel, we solve problems in mathematics, theoretical physics, and computer science in an environment that is completely free of politics, religion, economics, and ideology of any kind. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode on our channel that is of interest to you and use the comment sections under that episode, and I will take it from there. And of course, and as usual, I would like to extend my deepest gratitude to all the current subscribers and current supporters of our channel. In the mathematical problem S3E28, we're asked to evaluate a finite trigonometric sum whose common term is the inverse trigonometric function of arctangent. The argument of that function is a function that is rational in the summation index m that varies between 1 and n, where n is a whole positive number that varies over 1, 2, 3, 4, 5, and so on. And the argument of the inverse trigonometric function of arctangent has the following structure. In the numerator, we have twice the summation index m, and in the denominator of that function we have the summation index m raised to the 4th power plus the summation index m squared plus 2. And if you haven't solved this problem on your own yet and still want to give it a shot, then here is a hint. 2 is equal to 1 plus 1. Aside from its purely practical utility, one of the other reasons why it is a good idea to practice solving the problems in which we're asked to evaluate finite or infinite sums is because every time we face such a problem, we have to deal with the so-called open-ended problem. And among other things, of course, this is what grown-up mathematicians do. They deal with open-ended problems. Consequently, every time we take on the problem of summing or finding a way to sum a given finite or infinite sum, we put our mind into a mode that is isomorphic to the mode in which the mind of a practicing mathematician operates. And it follows that the more we practice such solving such problems, the better we prepare our mind for the bigger and better things to come. Consequently, since there does not exist a one industrial strength cookie cutting method for evaluating sums, finite or infinite, here is a short list, and by no means this list is all inclusive, of how we can approach the process of unfolding or generating an answer to the question of what is an alternative expression for this or that finite or infinite sum. We can try, for example, to construct a differential equation in which we, for example, equate our given sum to a function, take the first derivative of one side, take the first derivative of the other, somehow gain a competitive advantage from differentiating the sum, the terms of the sum, maybe constructing a fairly simple differential equation, and hopefully we can solve this equation. We saw that method in action in season 3, episode 20, when we solved the mathematical problem S3E28. You can find all this information using the season guide, the free PDF file. The link to that PDF files, the links to these PDF files are in the comment section to this video. We can also likewise try to construct an integral equation where we will integrate both sides and hopefully gain a competitive advantage, because an integral may be quite helpful and produce something that can be tactically acted on. We can also use the idea of the center of mass borrowed from physics. We saw this idea in action in season 2, episode 2, while we were solving the mathematical problem S2M2. Also, you can see it in season 3, episode 21, where we were solving the mathematical problem S3M12. We can also use the so-called multiply, subtract, and conquer idea. This is how we solve the problem of summing, for example, the infinite series shown over here. This is our favorite geometric series, if you will. We can also use the idea of double counting that is so popular in combinatorial analysis. I explained in detail how double counting works when we apply it to the process of summing certain series, finite or infinite. This is done in season 3, episode 9, when we solve the mathematical problem S3M6. We can also use the following idea. We can try to promote a numerical sum into a functional sum or series, find an expression for the functional series or the functional sum, determine the disk of convergence of that functional series, and then from the disk of convergence we yank an advantageous specific number and then demote back the functional series into a numerical series that matches the one sum that is given, and thus produce the answer. We can also use the ideas, for example, from the Fourier analysis, and the ideas that go back to Leonard Euler and Lagrange, who used this idea for summing certain series on the origin-centered unit disk. We can also use the Cauchy's residue theorem, according to which the integral of a certain function, let's say holomorphic, over a simple closed curve, a curve that is evidently closed, contains the origin, and has no self-intersections. This is a definition of a simple curve, and such an integral can be represented as the sum of residues of that function over the poles that are included by this simple closed curve, scaled by 2 pi I. And it so happens that most students, when they learn about this theorem, they only use the computational flow in this theorem from right to left, which means that what they do is they circumvent the process of traditional integration by simply computing the residues of the given function that is holomorphic everywhere in and on the chosen simple closed curve that contains the origin, and then they simply sum these residues, multiply it 2 pi I, and the game is over. But the Cauchy's residue theorem is so versatile that the computational flow in that theorem can be flipped to the opposite and be used from left to right, where we actually carry out the converse task. We compute the integral in some other way, but we manufacture the residues of a function in such a way that these residues match the given sum, and that sum could be finite or infinite depending on how we chose the simple closed curve over which we integrate the given function. This curve can include a finite number of residues or infinite number of residues, but anyway, the idea is to coalesce the residues of the function into the given sum and thus compute the integral, and voila, produce the value of the sum. So after this is how we evaluate the following sum on this channel: 1 over n squared from 1 to positive infinity. And this is precisely how we do it on this channel. Find the episode where we do it, and this is exactly the idea that we exercise over there. Our simple closed curve will be a system of squares over which we integrate a certain function. And finally, we also can try to elicit the telescopic structure of a given sum. It may happen, it may not. We show how the telescopic structure of a sum can be exercised or exposed in season 3, episode 3, when we solve the mathematical problem S3E28. And again, when we cast our eyes on a given problem, none of these approaches are guaranteed to work. And this is precisely, in some sense, the fun part of trying and failing. But the trick is, or the idea is, that while we cycle in our mind through ideas that can help us evaluate a given sum, we are precisely doing mathematics, or we are thinking like or acting like a mathematician. And it so happened that maybe you can take any of these ideas and carry them through to success with this particular problem. But for example, when I was looking at this problem, constructing a differential equation, I don't know, this is kind of put me off. If we say this is a certain function, then the first derivative, just the first derivative of the common term over here is what? 1 over 1 plus this argument squared. We have to square the trinomial, and then this already makes my liver quiver. So I figured, okay, this is, I will not pursue this approach or this approach. For example, if we integrate both sides of a certain relation, then the integral of this thing does not look very enticing, even though, who knows, maybe if we put some effort into it, we can take it further. The idea of the center of mass. Also, when we use the notion of the center of mass to sum certain series, we usually try to cook up a configuration of point masses in such a way that this configuration is symmetric, and we can obtain or figure out what the center of mass of this discrete and finite system of points already is by other means. And through that symmetry of the arrangement of point masses, we can find the location of the center of mass and then compute the sum. Also over here it did not work, but it turns out that precisely through this hint over here that 2 can be represented as 1 plus 1, it turns out that it can be shown that this here finite trigonometric sum possesses precisely a telescopic structure. Remember that in problem solving there are no guarantees of any kind, especially no guarantees of success, and quite the opposite is actually true in most problem solving sessions. It's almost guaranteed that we will fail, so we should have enough, we should possess enough of an intellectual stamina in order to be ready, prepared, and willing to try something else when we fail with the current idea. So if we have a good reason to suspect that this here finite trigonometric sum possesses a structure that is telescopic, then how do we show that the sum is telescopic? Well, usually we want to show that a given term, a common term of a given sum, can be represented as a difference, something minus something, and at some point again this very something will show up with the positive sign. So these two somethings that are equal in magnitude but have opposite signs cancel out, and we hope that many or most of such terms will cancel out and a small number of residues will be left over, and the sum of this small number of residues is what many people refer to as the closed form formula, the so-called closed form formula, or as I like to put it, an alternative expression, a synonym for a given sum. So here, what is the simplest way to represent, to elicit this something minus something? Well, when we deal with trigonometric functions, it's usually the sum and difference of the usual suspects at hand. So if we have the inverse trigonometric function of arctan, then what comes to mind? The difference, arctan of one thing minus arctan of the other. But how do we roll all these ideas into actionable mathematics? Well, here, depending, you may remember, I usually do not remember these things, and if need be, you can hone in and eventually come to understanding of how these things work as follows. Let's say we take it as a starting point that you may remember that for all real numbers, alpha and beta, for which the tangent of the angle alpha, the tangent of the angle beta, and the tangent of the difference of these two angles are defined in such a way that the denominator of this ratio is never 0. Here we have tangent alpha times tangent beta. Then the natural tendency over here is to do the following. If we put x equals tangent of alpha, then from here we'll follow what? That the arctan of x will be alpha, and if we put y equals tangent of beta, from here we will say that arctan of y is equal to beta, give or take. We have to be careful over here, and here is why. Let's say we apply the arctan to both sides of this relation. Then what we will have? We will have the arctan of tan of alpha minus beta equal to arctan of what? Let's see. The tangent of alpha we already designated with x, tangent of beta we designated with y, so we'll have x minus y divided by 1 plus the product of these symbols, x times y. And now we have to carefully resolve this situation over here and transition from here into a working formula. But when we do this, we have to be careful. We cannot blindly just remove all the symbols and come to the difference alpha minus beta, or take it as arctan x minus arctan y. Why is that? Well, let's do this. Recall that if we were to construct a graph, a partial graph of the function, let's call it arctan of tangent of x, this will be x, then what will this graph look like? Think on your own and then compare your idea to ours. Here, the deal is the following. This graph will look as follows. Let's say this is this point right here is pi over 2, and this is negative pi over 2. Then what will the graph of this function look on this subset of real numbers? So here it will be a square, evidently. So this is pi over 2, this is negative pi over 2. It goes like this. So what will the graph of our function arctan of tan of x be? Well, it will be a line segment with its edges punctured out, and that line segment, when projected, this side projected, will produce pi over 2. This side will produce negative pi over 2. What will happen next? Well, over here we will have another beginning of this line segment like this. It will run like this. This will be pi. This will be pi. This point over here will be 3 pi over 2, and to the right, to positive infinity. This is how this graph will run, and the same thing will happen over here. Punctured out. Here we will have the point negative pi. This point will be negative 3 pi over 2, and so on. Periodically extended. This is what the graph of this function will look like. And the important thing to understand here is that the value of this function will depend on exactly where the argument x falls within this segments that are delineated by what? By, let's say, odd multiples of pi over 2. And in general, our function will unfold as follows. The arctangent of x will be represented as follows. Will be represented as x minus k pi, where we have the following deal: minus pi over 2 plus k pi, and x is less than pi over 2 plus k pi, and the index k varies which way? Well, k varies over 0, and then plus minus 1, plus minus 2, plus minus 3, plus minus 4, and so on. So carefully you will understand over here the following with k. When k is equal to 0 and x varies between strictly pi over 2 and negative pi over 2, then arctan of 10 is equal to x, and this is precisely what we have. For k equals 1, we will have this thing over here, and this will be what? This will be x minus pi, and if we move into this direction, it will be x plus pi, and so on. And that means that when we unfold this side of this relation carefully according to this formula over here, we will obtain the following result for the difference alpha minus beta, or arctan x minus arctan y. The set difference splits into three cases depending on precisely how the arguments to these two functions, x and y, interact with each other, and this interaction is captured in these three cases over here: 1, 2, 3. Namely, the difference between the arctan x and arctan y comes out to be precisely the arctan of x minus y over 1 plus xy, our original expression that I showed in the previous segment a few seconds ago, if the product xy is strictly larger than the negative unity. The same difference comes out to the positive copy of pi added to this here arctangent if x is strictly positive, but the product x and y comes out to be strictly less than the negative unity. And lastly, this difference of arctangent comes out to be negative pi plus the same arctangent if x is strictly less than 0. Here the sign flips to the opposite, less than versus greater than, less than 0, but the product x and y is strictly less than negative unity. And my previous segment was in some sense a lightweight motivation to see why and where from this relation over here comes from. But if there will be enough of interest in the audience, if you guys want me to, I will just let me know in the comments. I'll put together an episode that proves this split into three cases more formally with all the detailed analysis. And the way we do it, we actually start working on the difference between not the arctans, but not between the arctangents, but between the arcsines, arccosines, and then we come to arctangents. It's not too complicated, but it's just a little bit of a detailed and careful work with the signs and quadrants in which angles come out to be. But in our case, we see that what is about to happen precisely because of my earlier hint. The two can be represented as sum of 1 plus 1. Let's look at the structure of the denominator. We want to have, when we juxtapose what we have against what we wish for, this is our wishful thinking, remember. Nothing is guaranteed. This is just our wishful thinking. So we think that the denominator of this arctangent should match the denominator of this arctangent, so we can capitalize on this and hopefully elicit the telescopic nature of this here sum. We should have the following: 1 plus x times y on the one hand, and precisely because 2 can be represented as 1 plus 1, we will have what? 1 plus m raised to the 4th power plus m squared plus 1. So this is what we need. This is what we have. If we equate the two, what will happen? square of a, let's say, real number, another square of a real number. So positive, positive, positive. The sum of all numbers is positive. So this product must be positive. What's the easiest or most convenient thing for us to do? Well, the easiest, most convenient thing for us to do is to take these guys to be positive. This will definitely hold true. The product of positive numbers will definitely be greater than the negative unity. And then basically we pick this branch of this three-way split. And in our computations, we just want to keep ourselves honest and validate this requirement during our computations. And just to be pedantic, I want to remind you guys one more time that an idea in mathematics is the first class citizen, and this process in real time, when we try and fail several times, but then we converged on a successful idea, that was mathematics with the capital M. Whatever follows this idea is either lesser mathematics or not mathematics at all, something like a mathematically flavored activity which carries our idea through. And then sometimes the process of validation or invalidation of this idea also requires some amount of ingenuity. So take my claims that what follows an idea is not mathematics with a grain of salt. So here we already understand all the motivation for replacing the arctan of this here horrible looking argument with the arctan of what? X minus y over 1 plus x times y. So when we equate two functions by our wishful thinking, we equate its argument. So essentially what we want to have over here is the following. We want 2m over m raised to the fourth power plus m squared plus 2 to be equal, by our wishful thinking, to x minus y over 1 plus x times y, where these magic numbers x and y honor the following constraint. Their product is strictly larger than negative unity. And how do we carry this wishful thinking into real life, into practice? Well, what we do here is the thing that is very similar to what we do with complex numbers. When we have two complex entities that are equal to each other, the usual tactical maneuver to extract some actionable mathematics from this situation is to equate the real parts of this equal something to each other and separately equate to imaginary parts, and then derive some tactical benefit. Here in this case, when we want to impose this equality by our brute force or by our will, we will do the same thing. We will equate the numerators of two fractions to each other, and separately we will equate the denominators of these two fractions. And from that maneuver, the following thing will happen. We will say that on the one hand 2m must be x minus y. On the other hand, let's do this right away. Well, let's be diligent students of mathematics and do it carefully. Plus 2 equals 1 plus x times y. Over here, right away, we see 1 and 1 cancel out. So from this, we, let's say, carefully go into this. So we will say that x is equal to what? 2m plus y, and then xy, the product xy, must be equal to m to the fourth plus m squared plus 1. That maneuver is understood. X is known. So what do? Evidently, without thinking too much, we put x over here. So we have, on the one hand, we have 2m plus y times y. And what is this? Well, this, let's spell it out right away. Y squared plus 2m times y. You see, y squared plus 2m times y. And then we carry this horrible thing to the other side. So we will say minus m to the fourth minus m squared minus 1 is equal to what? Is equal to 0. So with respect to y, we have our favorite quadratic equation. Such equations can be solved algebraically. That is what most people know how to do, but actually this sort of equations, the quadratic equations, can be solved purely geometrically with the so-called Carlisle circles. And maybe I will put an episode together that explains how to do it. But for now, we just plow right through by brute force and we write down the following expression. Let's compute the discriminant of this equation. The discriminant will be, let's do this, it's b squared 4m squared minus 4 times the coefficient by the most senior power and the free floating term. So we will have plus 4m to the fourth plus 4m squared plus 4. What do we see over here? Well, we will see that 4 is present as a factor everywhere. So when we factor it out, we get m to the fourth plus m squared plus 2 copies of m squared and plus 1. And look at this, the discriminant comes out to be a perfect square, m squared plus 1 squared, a perfect square. So once we write down the roots of this equation, y1, 2, it will be negative b coefficient to m over 2. So it will be minus m plus minus, and then square root of the discriminant will be 2 divided by 2. The factors are gone, so here we will have just the square root of the denominator, which is m squared plus 1. In other words, we have the first root, let's say it will be minus m plus m squared plus 1, and then the second root will be negative m squared negative 1 negative m. Look at this. The thing is, it turns out that due to our constraint, see, we have to honor this constraint at all times in our computation. So this constraint bears heavily on all the decisions that we make in this analysis. But it turns out that regardless of which value of the root of this quadratic equation we pick, this one or this one, the constraint will hold. So for simplicity, and I'm pretty sure that most people, when they see this, they are not going to go with it right away. They will go right away with this. This is a pleasant expression. So we have, let's put it this way, if we know what y is, do we know what x is? It's y plus 2m, and we have negative 2m over here. So let's write down the x as a function of m will be what? M squared minus m plus 2m will be plus m plus 1, and y we pick as a function of m as m squared minus m plus 1, some sort of vague conjugate of x. And if we go with this choice, ideally, I will not do it right now for you. I will not insult your intelligence. This is sub-middle school arithmetic, but I recommend that you carry through this exercise on your own, on the side somewhere, on a different piece of paper. Multiply x times y, multiply this trinomial by this trinomial, and prove to yourself that this constraint is honored by this choice of the root y and the corresponding value of x. I also recommend that you carry out the other test. You take this value of y, this root where all things are negative, compute the corresponding value of x to m, and then multiply this value of x with this value of y and prove to yourself that this constraint is honored. But now, once we obtained this result, we want to show that this, what are these things? These things are the arguments to our arctangent. So we want to show that in this argument, the telescopic nature of what unfolds when m varies over 1, 2, 3, 4, 5, and so on is present. That is trivial to do by iterating the value of the summation index m rightward once by replacing m with m minus 1 in this here function. And once we do that, we see the following. Instead of m and m everywhere, we inject m plus 1, and we have m plus 1 squared minus m plus 1 plus 1. This is baby arithmetic. Remember my comments that is what follows is not mathematics, but lesser mathematics, or just computational calisthenics, if you will, a mathematically flavored activity. But we have 2m plus 1 minus m minus 1 plus 1. So what do we see? We see that this one and this one cancel each other out, and this negative m and positive 2 copies of m cancel. We have what? M squared plus m plus 1 plus m plus 1. And what is this? This is precisely x of m. That means that once we iterate in our sum rightward once from m to m plus 1, in the second part, when we subtract the arctangent of this argument, we will have precisely the arctangent of the first summed in the previous iteration. In other words, let's put it this way. If we have, let's say, I will designate this for the sake of brevity with the uppercase A, just to be short, concise, and to keep it easy on our eyes. So at the mth iteration, we will have f(a) of m plus a of m plus 1, and this will come out to what if we keep our x's the same. So it will be a of x of m minus a of y of m plus a of x of m plus 1. You see, this is how we iterate once. The first split summoned, the second split summoned, minus a of what? It will be of x of m. Remember, we just showed that y of m plus 1 is the same as x of m. So this is precisely, so this time the smallest distance, if you will, between two terms that have the same magnitude but different signs, or the terms that cancel out, is 2, because 2 summons over here sit in between, the monkey in the middle, if you will, and these two guys cancel each other out. Cancel and cancel, you see. And this primes this little engine that could, the telescopic engine that wipes out most of the terms. So now let's say we will designate our sum as sigma n, is this guy right here, the sought after sum. So we will have for the sum the following expression. Sigma n will be the sum over, what is it, m from 1 to n, but here we will have the following difference. Arctan of what? Of this guy, m squared plus m plus 1 minus arctan of m squared minus m plus 1 plus 1. You see, this is our transformation. The original sum, the transformed sum, but here the telescopic nature was revealed, was unmasked through our manipulation and a brave idea, motivated by the fact that 2 is a sum 1 plus 1, and then the rest followed. So now again, keeping it easy on our eye, I will designate the arctan as just uppercase A. We understand what that means, so I will carry the computation over here. Let's do this together for the few first terms. When n is equal to 1, what we will have? 1 plus 1 plus 1, we will have arctan of 3 minus 1 minus 1. This will be 1, arctan of 1. So this is our first pair. Plus, what will be next? 4, 6, 7. 7 minus 4 minus 2. 2 plus 1, 3. So it will be minus a plus 3. You see the smallest distance with these guys? Okay, so this was m equal to 1. So this is m equal to 2. Let's do 3 together. So what we will have when m is equal to 3? 9, 12, 13. So a of 13 minus a of what? 3, 9 minus 3, 6 plus 1, 7. Plus 1, 7. You see, this is m is equal to 3. Again, what happens? These two guys over here cancel, and then this guy, arctan of 7, will cancel with the arctan of 7. And this wave of cancellations will carry through. So arctan of 13 will cancel out with the arctan of 13. At some point, this is the guy that seems to be the survivor, but after we do this several times, at the end, what we will have? We will have arctan of n squared plus n plus 1 minus arctan of n squared minus n plus 1. And that will be it. Remember, our sum is finite. So at some point, we will have this. But remember that the terms with the negative sign in front of them, they all cancel out. So this guy eventually will cancel out. And our sum will degenerate into what? Technically, it will still be a sum, still a finite sum. But this sum involves only two terms, which in some sense, the larger the n over here, the more shows that in some sense we have one. We managed to reduce a potentially long sum into just a sum of two terms. And what are these terms? Well, it will be arctan. I unfold uppercase A into its official name. It will be arctan of n squared plus n plus 1 minus arctan of 1. And what is the arctan of 1? This is the synonym for, if we take the principal branch, is pi over 4, and we're pretty much done. If we designate our sum with the lowercase sigma, n is the sum that runs over the summation index m from 1 to n, arctangent of 2m over m to the fourth power plus m squared plus n1. We now know that an alternative expression or a synonym for the sum is given over here in the upper right corner of your screen. Arctangent of n squared plus n plus 1 minus pi over 4, which is a synonym for the arctangent of 1. And this pretty much will be in your blood already the moment you compute the so-called partial sum, because this is what we have over here, a partial sum. You already know the answer to the question: does the corresponding infinite sum or infinite series converge or not? And the answer is, in the traditional sense, if we discard for a moment the other alternative ways to evaluate the convergence of or divergence of classically convergent divergence of the classically divergent series in the classical form, whether this series converges or not. And in this case, it does, because then our corresponding series that runs from 1 to positive infinity of pretty much the same summons comes out to the limit of the partial sum. The limit of the partial sum here, see, this is the beauty of being able to solve these questions and answer this solve these problems and answer these questions. The limit of this partial sum will be precisely the limit of the difference by the corresponding theorem from real analysis or mathematical analysis, however these courses are called in your country. The limit of the difference is the difference of the limits, provided that the limits exist. And in this case, the limits do exist. The limit of the constant pi over 4 is pi over 4. And what is the limit of this arctangent when the principal branch, remember that the function arctangent, in some sense, when you learn these things for the first time, sort of breaks your normal notion of a function has not one branch, but infinitely many branches. This is the so-called principal branch, and then on top of that branch, there is stacked infinitely many like branches. They go into the positive infinity, and below it, there are stacked infinitely many branches that go into the negative infinity. But as far as the principal branch of the function arctangent is concerned, that branch is bounded both from above by pi over 2 and from below by negative pi over 2. So when x tends to negative infinity, then the value of the arctangent tends to negative pi over 2. When x tends to positive infinity, then the value of the arctangent tends to positive pi over 2. Consequently, in our case, we have positive, positive, positive. The whole thing is positive. this term over here, in a sense, outpaces the rate of growth of this term outpaces all the other one. The constant can be dropped when n is large and positive. And there you go. Lo and behold, in the limit, our partial sums come out to pi over 2 minus pi over 4 is pi over 4. And we have this wonderful result over here that the corresponding infinite sum converges. And not only that, we know that it converges, we can actually give the name of the real number to which this series converges. The name of this number is pi over 4, but that is not it. There is more. If you understood what just transpired, then you can take on the following two simple sums that, in a sense, you can already construct yourself. If you understood the basic principles according to which we solve the problem S3E28, then you should be able not only evaluate the sums that you see on the left side of your screen by yourself, but you also should be able, as a fun experiment, to construct more like sums. In the first sum that you should try to evaluate by yourself, we have the same inverse trigonometric function of arctangent, where the summation index k varies over 1, 2, 3, 4, 5, 6, 7, and so on till n. And the argument of this arctangent is the following: x in the numerator and 1 plus k, the summation index, times k plus 1 times x squared, under the assumption that the argument x is strictly positive real number. And in the second sum that you see over here, we also have the summation that is carried out with respect to the index k that varies from 1 to n, and a whole positive number. And the argument of all the arctangents in this sum is r in the numerator, and in the denominator we have 1 plus a k times a k plus 1, where the numbers a k form an arithmetic progression with a common difference of r, under the assumption that the first element of our arithmetic progression, a1, and the common difference are strictly positive or greater than 0. And again, remember that the actual answers or synonyms or the alternative expressions, the closed form formulas, if you will, for the sums are not as important as your ability to generate a convincing and perhaps an elegant, creative, crisp story behind why the alternative expressions for these sums are what they are. And for a reference with the correct response, one way to record these answers is as follows. And this will be it for the mathematical problem S3E28, and we will move on to a new challenge next. Our next challenge will be a problem in mathematics S3E16, and the objective of this problem will be the following: using the art of manipulation of inequalities, evaluate the following limit, where the expression to evaluate has the following structure: the whole positive number n raised to the power of 1 over n. Again, n is a whole positive number that varies over 1, 2, 3, 4, 5, 6, 7, and so on, under the condition that n grows without upper bound or tends to positive infinity. Again, make sure you understand the objective of this problem. Evaluate this here limit not in any which way, but precisely using the art of manipulation of inequalities, because in US, for example, this author of this book precisely claims that the calculus of limits is the art of manipulation of inequalities. See if you have what it takes. And this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the mathematical problem S3E16.